Hello and welcome to problem set number 9. Our topic today is Lewis structures, electron pair geometry, and molecular geometry. Before we get started, if you have not already done so, I would recommend that you do print out the worksheet to accompany this problem set. If you don't have it in front of you, I will be reading the problems so you can still follow along fairly easily. Okay, number one. Number one is a multi-step problem, A through G. Draw a Lewis structure to represent each of the following molecules. A, ammonia. I know we did this one in the tutorial, but hopefully it will help you to go ahead and just work it again, just more and more practice. Okay, so I'm going to follow the 5 rules that I presented in tutorial 9. Rule number 1. Add up all your valence electrons. So nitrogen has 5, and each hydrogen brings 1, but there's 3 hydrogens, so 1 and 1 and 1 makes 3, so a total of 8 valence electrons. Rule number 2, show single bond connectivity between the atoms. We know that the hydrogen have to be terminal, so not so hard for this one. We know that the hydrogen can only have 1 bond, which puts nitrogen in the center. Rule number 3, complete octet on the outer atoms, not the central atom. So that would be hydrogen. Well, hydrogen has achieved a full valence shell when it has just 2 electrons, and a single bond represents 2 electrons. So our hydrogen already have their form of octet, okay, their full valence shell. So I'm going to write Na. We're not going to change anything based on rule number 3. Rule number 4. If there are valence electrons left over at this point, you're going to put them on the central atom. The central atom being nitrogen for this example. So we have 8, and we've used 2, 4, 6. Well, we have 2 left over. Let's go ahead and put a lone pair on nitrogen. So our Lewis structure now looks like this. Rule number 5 tells us if the central atom is still not satisfied with octet, form double or triple bonds. So let's check the central atom. Nitrogen has 2, 4, 6, 8. So we're done. Rule number 5 will not apply here. So let me write 5 Na. We had our final answer on step 4. Okay, B. We're going to draw a Lewis structure for water. Okay, H2O. So step 1. Add up all your valence electrons involved in bonding. Oxygen has 6. Each hydrogen brings 1, but there's 2 hydrogens, so that's 2. So we again have 8 valence electrons, just coincidence, it is the same number. And now we're going to show the single bond connectivity. Hydrogen has to be terminal. All right, step number 3. Complete octet on your outermost atoms, not the central atom, but the terminal ones. So those are both hydrogen. So they are complete with just a single bond, 2 electrons being shared. So I'm going to write Na again. Don't worry, we will get to problems where step number 3 will apply. Number 4, if there are any electrons left over, put them on the central atom. So we have 8 total that we're working with. We've used up 2, 4. We have 4 left over. Okay, we're going to put them on the central atom. That is oxygen. Put them on there as lone pairs. So now our Lewis structure looks like this. Step number 5. If octet is still not satisfied on your central atom, form double and triple bonds as needed. So 2, 4, 6, 8. Oxygen has a complete octet. In fact, it follows the bonding pattern that we would expect, what we talked about in tutorial number 9, with 2 bonds and 2 lone pairs. So for rule number 5, not applicable, we actually had our final answer on step 4. Again. All right. C. Carbon tetrachloride. All right. Rule number 1. Add up all your valence electrons. Carbon is in group 4A, has 4 valence electrons. Chlorine is a group 7 halogen and has 7 valence electrons, but there are 4 of them. So that is, that's 28. 4 times 7. Okay. So we get 32 valence electrons that have to be accounted for in our final Lewis structure. All right, rule number 2, single bond connectivity. Carbon is going to be central. Think about that. You should know that for a couple of reasons. One, because there was a tip in tutorial 9 that told you that typically your central atom is going to be the one that there is only one of or the fewest of. Okay, so that would be carbon. The second thing that might have helped you with that is that you know the bonding pattern. You know that carbon likes to form 4 bonds, and you know that your halogens like to form just 1, which means they're typically going to be terminal like hydrogen. Okay, so we've got carbon in the center with 4 bonds, have to be carbon, and the chlorines terminal with just 1 bond. Makes sense. Okay, rule number 3, we're kind of running out of room here. Rule number 3, let me draw a line here so we don't confuse it with B. Okay, rule number 3 tells us to complete the octet on our outermost atoms, not the central. So right now each chlorine just has 2. That is not a proper octet for a chlorine atom. Chlorine needs 8. Okay, so we're going to have to add 6 more electrons in the form of lone pair of electrons. So that's 3 pairs. Let's do that here. So 2, 4, and 6. 2, 4, and 6. Remember that the single bond already shows a set of electrons, so 2, 4, 6, 8, so octet. But we're only adding 2, 4, 6 for step 3. Okay, got to add it to all of them. Rule number 4, if there are any electrons left over at this point, you're going to put them on your central atom. So we have 32 to work with. We have used up 8, 8, 8, and 8. See, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, so 8 times 4 is 32. We've used them all. We can't do anything for step 4. We don't have any valence electrons left over. Okay, step number 5. If octet is still not satisfied on your central atom, form your double and your triple bonds as needed. Let's check on carbon here. 2, 4, 6, 8. Octet is satisfied. So nothing to change on step 5. We were actually done with this problem on step number 3. Okay. I think we have room to squeak in one more here. So let's do D, carbon dioxide. Add up your valence electrons for rule number 1. Carbon is a group 4 nonmetal, means 4 valence electrons. Oxygen is a group 6 nonmetal, so 6 for each oxygen. There are 2 of them, so that's 12. So the total is 16. Okay. Step number 2, single bond connectivity. We're going to put the 1 carbon, the one that there's fewest of, in the middle. Step number 3, complete octet on your outermost atoms, not the central one, so that would be the oxygen in this case. So we're going to complete their octet by adding another 2, 4, 6. So it totals 2, 4, 6, 8. 2, 4, 6. Okay. Step number 4, if there's anything left over, any valence electrons left over, you're going to put them on the central atom. So let's check here. We have 16 to work with. We've used 8 plus 8. We've used all 16. So not applicable. But clearly we are not done because carbon is not going to be happy with just 2 bonds. Okay, so 2, 4 electrons. It needs 8. So that's going to be taken care of in step number 5. Form double and triple bonds as needed to complete the octet on your central atom. Okay, so for carbon, let's go ahead and redraw this here. Go to the blue pen. We're going to pull in a set of lone pair of electrons and share them between the atoms, forming a double bond. We're going to do the same thing over here. we know that oxygen likes to have 2 lone pairs and 2 bonding pairs of electrons. So we're not going to pull in 2 lone pairs from one oxygen, which would leave it with just 1 lone pair and form a triple bond, 3 bonding pairs. We're going to pull 1 lone pair off of each so that each oxygen is following the expected bonding pattern for an oxygen atom, or a group 6 atom. Okay, so our final answer looks like this. Okay. All right, so we're going to need these Lewis structures for number 2. So I'm going to erase everything except our final answers here. Okay, E, hydrogen cyanide. Step number 1, we're going to add up all the valence electrons involved in this molecule. So hydrogen just brings 1. I'm going to go ahead and write these all out. Carbon, group 4A, brings 4 valence electrons. Nitrogen, group 5A, 5 valence electrons. So we've got 5 and 5, we've got 10 total. Step 2, single bond connectivity between the atoms. They're typically, if there's one of each, they're going to be written in order of connectivity already. So we can expect hydrogen bound to carbon, bound to nitrogen for rule 2. Rule number 3, complete the octet on the outermost atoms only, not the central atom at this point. So hydrogen is satisfied with just 2 valence electrons. Remember that it only has a first energy level S sublevel with 1 valence electron, and that first energy level S sublevel can only hold a maximum of 2, so it is filled when it has 2 electrons in it. So 2 electrons here in the single bond completes the octet for hydrogen. Okay. Nitrogen, however, needs 8. So I'm going to add 2, 4, 6, and there was 2 here, so that makes 8. Rule number 4, if there's anything left over, it's going to go on the central atom. So in this case, that's carbon. So let's check and see what we have. We have 10 to use. We've used 2, 4, 6, 8, 10. So we have 0 left over. So rule number 4, I'm going to write Na, not applicable here. Step number 5. If octet is still not satisfied on your central atom, you're going to form double or triple bonds as needed. So let's rewrite what we have here. Carbon only has 2, 4. It needs octet, so it needs a total of 8. So let's go to the blue pen. We can't get any electrons from the hydrogen. All its electrons are already being shared with carbon. It has nothing more to give, but the nitrogen can share this lone pair, which would give carbon 2, 4, 6. Not enough, it needs 8. Pull in another set to make a triple bond, 2, 4, 6, 8. So let's write our final answer here. Hydrogen and carbon have a single bond between them. Carbon and nitrogen have a triple bond between them. And nitrogen, as we would expect from those general bonding pattern guidelines, has 1 lone pair and 3 bonding pairs of electrons. So there's hydrogen cyanide. All right, so let's go ahead and erase all of this except the answer, and that one is E, because remember we need these Lewis structures to do number 2. So let's erase everything but the answer here. F. Okay. Phosphorus trichloride, PCl3. Rule number 1, add up your valence electrons. Phosphorus is in group 5A, so 5 valence electrons. Each chlorine is in group 7, and therefore each chlorine has 7 valence electrons. So 7 times 3, because there's 3 of them, is 21. Total of 26 valence electrons. Rule number 2, show single bond connectivity, and we're going to put phosphorus in the center here for a couple of reasons. 1, because we know, based on the tips given in tutorial number 9, we know that when there's only 1 of a certain atom, it's probably going to be your central atom. And also because we know that halogens tend to just form 1 bond and therefore are likely to be terminal. So it makes sense to put phosphorus in the middle for step 2, and your chlorine bonded to it. Step number 3, complete your octet on your outermost atoms, not your central atoms. So that would be for your chlorine. They each need to have 8. Currently they only have 2, so 6 more, written in as lone pairs of electrons, so 3 pairs. So let's recopy it down here. 1, 2, 3, 4, 5, 6. 2, 4, 6, 2, 4, 6. Okay. Step number 4, anything left over goes on the central atom. We have 26 to work with. We've used 8, 8, and 8. We've used 24. We have 2 left over, and so we're going to put them on the phosphorus, the central atom. I'm going to redraw that here. And step number 5 tells us if the central atom is still not satisfied, we're going to form double and triple bonds as needed. But we can see that phosphorus has 2, 4, 6, 8. So number 5 is Na, not applicable. Here's our final answer. All right, I'm going to label that as F and erase all the work we did so we can fit in our last one for number 1, which is G, sulfur dioxide. Okay, G, sulfur dioxide. Step number 1, add up your valence electrons. Sulfur and oxygen are both group 6 nonmetals. So 6 valence electrons, 1, 2, 3 total atoms with 6 valence electrons. So that is 18 valence electrons to account for. All right, rule number 2, single bond connectivity, putting sulfur in the middle. Rule number 3, completing the octet on our outermost atoms. That would be our oxygen. So 2, 4, and 6. We'll bring that to a total of 8. Step number 4, anything left over goes on your central atom. So we had 18. We've used 8 plus 8. We've only used 16. We've got 2 left over. And those 2 are going to go on sulfur. And step number 5, if octet is still not satisfied on your central atom, you're going to form double and triple bonds as needed. Let's go to the blue pen for this. Okay. So we've only got 2, 4, 6. So we're going to bring in 1 set of lone pair. And our final answer for sulfur dioxide will have a double bond to one oxygen and a single bond to the other. And don't forget a lone pair. Now we've got 2, 4, 6, 8. Doesn't matter if you brought the lone pair from this side or from this side. Notice that your final answer is going to look the same. Just pick it up, rotate it, set it back down, and it's on the other side. So don't worry about that. Okay, number 2. So let's circle this answer and label it G. And let's erase all of this work here. Okay, number 2. For each of the molecules in problem number 1, determine the electron pair geometry and the molecular geometry. So I went ahead and rewrote every single one of our Lewis structures out from problem number 1 because in order to analyze that 3-dimensional shape, that is the electron pair geometry and the molecular geometry. In order to analyze for that, we must have a proper Lewis structure first. So I went ahead and redrew those nice and neat here so we can refer back to those for problem number 2. Okay, so let's get started. So A is ammonia. So we can see that in our Lewis structure for ammonia, we have 3 bonds. So I'm going to write here 3 bonds. And 1 lone pair. So I'm going to write 1 lone pair of electrons. I'll just abbreviate pair and electrons there. Okay. So we've got a total of 4 charge clouds, 3 plus 1, total of 4 charge clouds. And remember that those charge clouds are going to repel maximum distance apart in three-dimensional space. For 4 charged clouds, that's going to be 109.5 degree angles apart. So these angles, including the angle between the lone pair and the bonding pair, will be 109.5 degrees. Okay. For an electron pair geometry, that is tetrahedral. So remember the electron pair geometry, I'll just abbreviate EPG for that, accounts for all of the charged clouds, and that gives a tetrahedral electron pair geometry. Anytime you've got 4 charged clouds, the electron pair geometry is always going to be tetrahedral, and those bond angles 109.5. All right, the molecular geometry, I'll just abbreviate MG for molecular geometry. The molecular geometry, remember, only looks at the atoms that are bound together and the shape that they take. So let's really think about what this looks like in 3 dimensions. It kind of looks here like we've got 90-degree angles. That's only because it's a 2-dimensional drawing. Let's go ahead and try to redraw this so that we can really see what's going on here with the shape. Okay, so if I put the lone pair and 1 bond in the plane of the white erase board, okay, so we've got a 109.5 degree angle here, not 90, so I purposely didn't draw it straight here, I drew it at an angle there, then that means that this hydrogen would have to be coming out of the whiteboard toward you, and another hydrogen would have to be going into the plane of the whiteboard, going away from us. Okay, so when we look at the molecular geometry, the lone pair does affect the bond angle and it does affect the geometry, the shape. However, we just look at the atoms that are bound together and we can see that the molecular geometry of the molecule is pyramidal. All right, so even if you draw your Lewis structure like this, and it looks like you've got 90-degree angles, it is up to you to understand that there are 4 charged clouds, therefore these angles are not 90, they are 109.5, which brings us to the molecular geometry that is pyramidal, because we do have 1 charged cloud that is a lone pair. All right, let's go on to water, H2O. We've got 2 bonds, and we've got 2 lone pair. So again, a total of 2 plus 2, or 4 charged clouds. So once again, we find that we have an electron pair geometry with 4 charged clouds, therefore 109.5 degree angles, and an electron pair geometry known as a tetrahedral. Let's continue that line there. Okay. All right, so the molecular geometry for this example, we're not going to look at the lone pairs now. We're just going to look at the shape of the atoms bound together in the molecule. So I'm going to redraw this. Let's do it like this. Let's put the lone pairs in the plane of the white erase board for just now, okay? And then that would mean that one of our hydrogens would be coming out and 1 would be going in to the plane of the whiteboard. Okay, so this angle here between the 2 hydrogens is 109.5 degrees. And the shape, the molecular geometry, is a bent geometry. Because remember that the molecular geometry just looks at the shape of the atoms that are bound together in the molecule. Okay. All right, going on to C. Carbon tetrachloride. Thought we were on F for a second. Okay, so we're on carbon tetrachloride. We've got 1, 2, 3, 4 bonds and 0 lone pair electrons, at least on that central atom. I know you're probably saying, there's lots of lone pairs in there, but remember that the three-dimensional shape is with respect to the central atom. Okay, and how are those other atoms oriented around that central atom? So 0 lone pairs on the central atom, so that's 4 charge clouds once again, which makes our electron pair geometry once again tetrahedral. Okay, let's write it down here. EPG, electron pair geometry, tetrahedral. Okay. And because there are no lone pairs, the molecular geometry is also tetrahedral. If you want to try to redraw this and really show the three-dimensional shape, then we can show 2 chlorines in the plane of our white erase board. So that means that this bond angle here is 109.5, not 90, right? This was not showing 109.5 degree angles. This is showing 109.5 degree angle, which means that another chlorine is going to be coming out of that plane toward us, and another is going to be going into the plane of the whiteboard, going away from us. Okay. All right, so it would look a little bit more like that. Let me label this bond angle in black. The blue would blend in a little too much. I'm going to do that right here too. I think the blue just blends in just a little bit too much. Okay, 109.5 degrees. Okay. All right, going on to D, carbon dioxide. We have 2 bonds. Doesn't matter whether they're a single bond or a double bond or a triple bond, each just counts as 1 charge cloud. So this counts as 1 charge cloud here, this is 1 charge cloud here. So 2 bonds that are 2 charge clouds, okay? Number of lone pairs on our central atom, 0, no lone pair. 2 charge clouds about our central atom here, carbon. And the maximum distance apart that 2 charge clouds can be in 3-dimensional space is 180 degrees, okay? So that gives us an electron pair geometry that is a linear. They're all just going to be in a line. And a molecular geometry, because there were no lone pairs, is also going to be the same as the electron pair geometry at 2 is going to be linear. Okay, hydrogen cyanide. So we have 2 bonds. Remember, it doesn't matter if it's single bond, double bond, or a triple bond. It counts just once as a charge cloud. Okay, so 2 bonds. And no lone pairs with respect to the central atom. So 0 lone pair electrons. So total number of charge clouds, again, 2. Which causes this angle to be 180 degrees. And creates a linear electron pair geometry and a linear molecular geometry. So I'll write EPG linear and molecular geometry, MG also linear. Okay, phosphorus trichloride. We've got 1, 2, 3 bonds. and one lone pair on the central atom. So one lone pair of electrons. So a total of 4 charge clouds. Okay, so that means that the bond angles, all of these angles here between our charge clouds, are 109.5 degrees. That's always the case when you have 4 charge clouds, leading to an electron pair geometry that is tetrahedral. But when we look at the molecular geometry, remember we're just looking at the atoms in the molecule. Okay, so let's redraw down here what that's going to look like. If the lone pair and this bond are considered to be in the plane of the whiteboard, then that means that this chlorine atom would be coming out of the plane, and this final chlorine atom would be going into the plane of the whiteboard. And so we see that we would have a pyramidal molecular geometry. So Mg for molecular geometry is pyramidal. All right, last but not least, we have sulfur dioxide. We have 2 bonds about the central atom and 1 lone pair of electrons. For a total of 3 charge clouds. Okay, so remember that the maximum distance apart in 3-dimensional space that 3 charge clouds can get is 120 degrees. So the angle between all of these charge clouds is 120. Now we've drawn it as if it's 90, 180, 90, but that's just how we drew it in our Lewis structure. Now we're analyzing 3-dimensionally how it really looks, and they're all going to be around 120 degrees apart. Okay, so let's redraw that. Put our double bond to the oxygen here. So I'm trying to indicate a 120 degree angle between this charge cloud, the lone pair, and this double bond, this charge cloud here for the double bond, and then 120 degrees between those and this single bond as well. So all of these angles are now supposed to reflect 120 degrees. All right? So our electron pair geometry, when we have 3 charge clouds at 120 degree angles, is trigonal planar. Remember that everything is going to lie in one plane, and you're going to get that trigonal planar electron pair geometry. The molecular geometry is not going to be the same as the electron pair geometry because there's a lone pair. And remember that although the electron pair geometry accounts for all 3 charge clouds, including the lone pair, the molecular geometry is just looking at these atoms that are bound together and the shape that they take. Okay, the lone pair is important because it does dictate the bond angle as 120. If we didn't have a lone pair, that bond angle would be 180 and it would be a linear molecule. But because we have the lone pair, it takes up its fair share of space, pressing those bonding electrons closer together, 120 degrees instead of 180 degrees. And so our molecular geometry becomes just bent. Okay. So that concludes our problem set number 9. I hope you will consider tuning in to tutorial number 10. Thank you very much.